Welcome to Brain Vision.
Hi everyone, so what we have today is a vertical cylinder that is insulated with a mass of 10 kilograms of water that's inside, of which 6 kilograms is vapor. The mass of the piston is such that the pressure inside is at a constant of 200 kilopascals. We have a supply line of steam that's coming in at 0.5 MPa and 350 degrees C. What we're asked to find is the final temperature and the mass of the steam that is entered when all the liquid in the piston has vaporized. So some of the assumptions that we're going to look at right now is we're going to assume that it's an unsteady process since the conditions within the device are changing. We're going to assume that the expansion process inside the piston is quasi-equilibrium. Kinetic and potential energy are negligible, and there's no work interactions aside from the boundary work. And we know that the device is insulated, so there's no heat transfer, and it's negligible. So what we're going to do first is find the properties of the steam. We know that these tables, A4-A3, A6 in these textbook, can give us the pressures, and by using the pressures we can find the enthalpies. So we know that the pressure inside, we're going to say is P1 equals 200 kPa. And we know the quality is 0.6 because we have 10 kilograms total, and we know that 6 kilograms is vapor. So by using this equation here, we can solve for our enthalpy. So H1 is going to be equal to HF plus X1 HFG. Now using the values from the table, we can find HF and HFG, and we find that H1 is equal to 1825.6 kilojoules per kilogram. Similarly, we can do the same thing for P2. So we know that P2 at the final is going to be 200 kilopascals since it is a constant pressure piston, and we know that all of the liquid has evaporated, so all we're going to have is saturated vapor. So that means our H2 is simply going to be HFG, which is equal, our H2 is going to be Hg at 200 kPa, and that is going to be equal to 2706.3 kilojoules per kilogram. Now if we look at the incoming enthalpy, we know that the initial pressure is 0.5 MPa of the supply line. We know the temperature is equal to 350 degrees C, and using this information we see that Hi is equal to 3168.1 kilojoules per kilogram. So we know that the cylinder is going to only contain saturated vapor at its final state of 200 kPa. So we know the final temperature actually, and we can also get this from the table, and we're going to see that T2 is going to be equal to T saturation at 200 kPa, and this is equal to 120.2 degrees C, and that's actually one of our answers. So we saw that without really doing any calculation, just from the table itself. Now we're asked to find the mass of the steam that is entered. So what we're going to do first is define our system, and we're going to define the cylinder as our system, which is actually a control volume since there's mass. This is mass that's crossing the boundary, since you have mass coming in from the supply line. What we can do is actually make a mass and energy balance for the system. So first we're going to do our mass balance. So mass balance. And we see that M in minus M out is going to be equal to the delta in the mass of the system. And we're going to rewrite this as saying that Mi, which is the mass that's coming in, is going to be equal to the final mass minus the mass in the beginning. So now let's go ahead and do our energy balance. So energy balance. So we know that just by the definition that energy in minus energy out is equal to the change in energy of the system. And we can rewrite this and saying that MIHI, which is the energy coming in from the supply line, is going to be equal to the work, because remember that piston is going to move, plus M2U2 minus M1U1, right? The change in energy is going to be equal to the change in energy plus the work is going to equal to the energy that's coming in. And we're going to assume that Q, the heat transfer, is going to be 0 because the system is insulated. Now what we're going to do is we're going to combine this relation with our mass balance above. And what we're going to get is 0 is going to equal W out minus M2 minus M1 HI plus M2U2 minus M1U1. We can now rewrite this as 0 equals a negative M2 minus M1 HI plus M2 H2 minus M1 H1. And the reason why we can do this is because we combine the boundary work and the change in internal energy into a change in enthalpy for, since we're having a constant pressure expansion or compression process. Since that piston, the mass of the piston is going to keep the pressure inside the same. So now what we can do is I'm going to solve for M2, and we'll see that M2 is equal to HI minus H1 over HI minus H2 times M1. Now remember that we actually know all of these quantities. We know HI, we know H1, and we know H2, and we also know M1 because it's given to us. So after we plug in those known variables, we get an M2 of 29.07 kilograms. Therefore, we know the relation between M2, M1, and the mass that's coming in. We know that Mi is going to be equal to M2 minus M1. We know M2, we know that M1 is 10 kilograms, so plugging those values in, we see that Mi is simply equal to 19.07 kilograms, and that is our final answer.